Hello class, welcome to our video notes lesson on Skill 8 from Unit 3, which is on applications of rational equations. And whenever we are applying something, typically that means we're applying it to some sort of quote, real world context. So this can be equated with word problems. So this will be our section on word problems that involve a rational equation, something where the variable is in the denominator. Now, a couple helpful hints to keep in mind as we are going through these examples are these relationships that we already know of as of right now. So whenever we're dealing with distance and rate and time problems, it helps to remember that the distance traveled of something is equal to the rate at which it's traveling times the time it took to travel. And so that helps to remember that. It also helps to remember the derivations of this equation. So another way you could think of this is rate is equal to distance divided by time. And that would be if I basically divided both sides of this equation by time. I'd be left with rate on one side and then distance over time on the other side. Similarly, I could say that time is equal to distance divided by rate. And that's, again, if I look at this equation up here and just divided both sides of the equation by rate, I'd be left with this little expression here. So these are related to this distance equals rate times time relationship. So it helps to keep them in mind. And then this one over here is very similar. So this is referring to when you're working and getting a job done or building something or cleaning something or painting something. The rate at which it takes you to complete one object times the time it took to complete, or the time you spent working, would equal to how much product you were able to create or produce. Very similar, right? Distance equals rate times time if you're moving and traveling. Product equals rate times time if you're working, okay? Now, just like with distance equals rate times time, I could come up with two different derivations of this one as well. I could say that the rate at which you are working is equal to the product you've been able to complete divided by the time it took you to complete it, okay? And again, that's from taking this equation and dividing both sides of it by time. Similarly, I could say that the time it takes for you to complete something would equal the product you produced divided by the rate at which you were working, and then that would tell how long it takes you to complete that product. So keep all of this in mind. It will help us as we are setting up our equations. Now, why would we be setting up equations? Because we're going to be working with word problems where the equation isn't given to you. So I always encourage my students that when you are confronted with a word problem, don't freak out, don't run away, but read it more than once, right? It might take 2 or 3 times until you really understand the context. I think once you can wrap your head around what's actually happening, then you can start trying to solve it. Then I always encourage you to underline the actual question part, the thing that's saying what is the, or find the, or how much will the, blah, blah, blah. Whatever the actual question is, you focus on that because that will help you decide what your variable should be. It's based off of what the question's actually asking. And then you will have to write an equation. This is always the hardest part, is getting that equation written down. It's going to be using the variable that you defined earlier, any numbers that were in the equation, and then for these types of rational equations, it's going to probably be requiring one of these 6 things. Distance equals rate times time, or rate equals distance over time, or time equals distance over rate, or any of these 3. We're going to be using them to write our equations in these particular contexts. Then you solve the equation. That part shouldn't be too bad. And then once you get your number, you answer the question. And again, this will be based off of, what the variable was that you defined earlier, and then you answer the question based on the number you got. So in number 1, here's the question. Okay, I'll read it out loud. You can follow along, but you might want to read it a couple more times to yourself after. But Michael can unload a delivery truck in 20 minutes. Hannah can unload the same size delivery truck in 35 minutes. This is if they're working separately. The question wants to know, how long will it take them to unload another delivery truck of the same size if they work together, right? That is the question. But even more importantly is this word long. How long will it take them? So that is wanting us to figure out the time it will take for them to unload a delivery truck if they work together. Now, so we read the question. So basically, this is telling us the time it takes for Michael and Hannah to unload a same size delivery truck on their own, right? It takes Michael 20 minutes. It takes Hannah 35 minutes when they're unloading a truck on their own. The question wants to know, how long would it take if they were unloading one truck together? Okay. So this is how long it takes Michael to unload one truck by himself, how long Hannah unloads one truck by herself. Question is, how long would it take to unload one truck together? So I'm going to define my variable. Okay, I'm going to define my variable. I'm going to say T is equal to the time it takes for Michael and Hannah to unload one truck together. Right? But I had to kind of read through it a couple times to kind of get that idea, that context. They've already unloaded one each. Question is, how long would it take for them to unload one together? And we don't know. So that's my variable. That's T. Okay. So I'm going to use the product equals rate times time setup. Now, I'm only looking for how long it will take them to do one truck together. So I'm not going to add products together because I don't want to get like 3 trucks or anything. I just want to know how long it would take them to do one truck. And then I'm not going to add the times together because if I added 20 minutes plus 35 minutes, that would be longer, right? It wouldn't take them longer to work together. It would take less time to work together. So what I'm going to add together are their rates. I'm going to put a little star over here. Okay. I'm going to say that Michael's rate plus Hannah's rate is equal to their combined rate. So Michael's rate would be he can unload one truck every 20 minutes. So this is product over time. And that tells me how his rate at which he can do this. One product every 20 minutes. Hannah can unload one truck of the same size. So I'm going to say same product, one truck divided by 35 minutes. So that's her product over her time. This is her rate. So this is kind of showing us like what fraction of the job each of them is completing. And then if you add their rates together, that'll give the combined rate, which would be one truck, right? Because they're going to unload one truck that's the same size. So we'll count it as being equal to these. But over their combined time, which is what we're trying to solve for. I don't know how long it will take them to do it together. So that's the variable. But I know that if I add Michael's rate with Hannah's rate, it'll equal their combined rate of change. So what we have here now is a rational equation. I've got T in the denominator. So I'm going to solve this with the methods that we had learned in the Skill 7 video. I'm going to start by finding the LCD of all the denominators. So it might help if I look at their factors. So I know 20 can break into 5 times 4, and then 4 can go further into 2 and 2. 35 can break into 5 and 7, and then T is just T. So I can see there's a common factor of 5. I only need that once, and then I need all of these remaining factors. So my LCD is going to equal 5 times each of the remaining factors. 2 2s, a 7, and a T. Okay? If I multiply all that together, I get 10 times 14, right? 5 times 2 is 10, and then 2 times 7 is 14, and then 10 times 14 is 140 T, because I also need to multiply by T. So this right here is my LCD, and I'm going to take that LCD and multiply it to both sides of the equation. So I multiply it to this side, and then I'm going to multiply it to all of this side over here. So that means I'll have to distribute. So when I do that, I get 140t times 1 over 20 plus 140t times 1 over 35 equals 140t times 1 all over t. And then I can simplify. 20 can cancel. It can go into 147 times. And then 35 has a factor of 5 and 7. And 140 also has factors of 5 and 7. And it leaves behind 4 and a t. So I have a 4 and a t left here. And then on this fraction, the t's cancel. And I had a t left here as well. So I get 7t plus 4t equals 140 is what I get when I multiply all of the fractions by the LCD. So then it turns into a very simple linear equation. And these terms both have a t, so they're like terms. I can add them together. So I get 11t is equal to 140, and then I can divide both sides by 11. And then it might help if I divide these numbers to have an idea of roughly how much time that is. So 140 divided by 11 is approximately 12.7 minutes, right? Because my units of time in the problem were minutes. So this was minutes here, minutes there. So that must mean this will be in minutes as well. Now, to answer the question, so I solved the equation, but now let's answer the question. So what is this 12.7 minutes? It's t. So then we have to look, what was t? T was the time it would take for Michael and Hannah to unload one truck together. So we'll say that it will take Michael and Hannah approximately 12.7 minutes to unload one truck together. That's how long it will take. So it saves time, right? If Michael does it himself, it takes 20 minutes. If Hannah does it herself, it takes 35 minutes. But if they put their forces together, it only takes them 12.7 minutes approximately, right? So the moral of this story is working together saves time. That is if you're working with somebody who doesn't distract you. So keep that in mind as well. Okay. I want you to try one. So this is going to be a little bit different setup because now I'm looking for a different time, how long it would take Dane to do a job himself. So kind of be aware of that. When you're setting things up, remember that if you add two different rates, it'll give you the combined rate. Okay. And then see if you're able to arrive at the correct answer. Okay. So let's see how you did. Now you can define the variable any letter you want. I chose T again, but hopefully whatever letter you chose represent how long it would take Dane to do the job himself. And then we're going to use a similar structure to our equation as our example where we add the two individual rates to give us the combined rate. And Colin's individual rate would be one driveway every 30 minutes. Dane's rate is one driveway every unknown amount of minutes. We don't know how long it takes him to do a driveway himself. And then this is their combined rate. So together it takes them 20 minutes. So one driveway every 20 minutes would be the rate, their combined rate. So then you have to find a lowest common denominator between all of the fractions and then multiply it to everything to cancel all the denominators. So between 20 and 30, the lowest common denominator is 60. And then since there was a t in this fraction, then our LCD also needs a t, so 60t. So I multiplied everything by 60t, so there ended up being a 60t in all the numerators, and which was able to cancel with all the denominators. So 30 goes into 60 twice, 20 goes into 63 times, and then the t's canceled there. So I was left with 2t plus 60 equals 3t, and then if you subtract 2t from both sides, you just get 60. 1t equals 60. So basically it would take Dane 60 minutes to shovel the entire driveway himself because he is Colin's younger brother, right? So the moral of this story is don't leave it to your younger siblings to do all the work, right? If you chip in, it only takes 20 minutes for the two to get the job done together. Like how awesome is that? So working together, helping each other out saves time. Moving on to our second and last example, a little bit more complicated problem here. So we've got a flight and there's some information, some pre-information before we actually start the question. But basically when you are flying across the US, it takes longer when you go from east to west than it does if you go from west to east. So flying from the East Coast to California takes longer than it does going from California to the East Coast. And we're assuming that winds are constant in the eastward direction. So what happens is when you're heading west, you end up going against the eastern wind. So we call it a headwind because we're going against the wind, and it actually slows the plane down. However, when you are flying eastward, so you're going in the same direction as the eastward wind, we call it a tailwind, and it actually increases the speed. So these are just some kind of facts kind of helping you understand what's going on in the problem. So here we're not going all the way to the East Coast, but we're going from Chicago to San Francisco. So east to west, and the distance is 1,850 miles. And then the time for a round trip from Chicago to San Francisco is 7 3/4 hours. So round trip, right? That's there and back. Now this 480 miles per hour is the airplane's speed without wind. So what it means by the airplane cruises at 40 miles per hour, that means that's the speed the plane is set to, the speed it would be moving at without any wind. Okay. And then we're going to try to figure out what is the speed of this eastward wind. We're assuming it's constant, right? What is this constant eastward wind? So since that's the thing we're trying to figure out, that's what we will go ahead and define as our variable. So I'm going to just let S equal the speed of the wind. Okay. Now for this question, the main piece of information that we're given is distance, 1,850 miles from Chicago to San Francisco, and time. But this is the total time, right? The total time is 7 3/4 hours. So I think I'm going to use time to set up my equation because that's the one I was given a total for. And basically, if you add the time it takes to go from Chicago to San Francisco, so time from Chicago to San Francisco, plus the time it would take to return, time from San Francisco back to Chicago, that would equal the total time, right? If I add up those two different times, that would tell me the total time it took to go round trip, right? This is round trip. And I know that piece of information. I know that it's 7 3/4 hours. So I know that whatever I get in my equation is equal to 7 3/4 hours because this information was given. I just need to get an equation or like an expression for the time from Chicago to SF and then a time from SF to Chicago. So I'm going to use this fact from earlier that distance is equal to rate times time. So if I want to get time alone, which I do, I just need to divide both sides by rate. So time is equal to distance divided by rate. And by the way, another word for rate could be speed because it's telling how quickly something's moving. So you can think of that word rate as speed. And we're going to have to think of it that way in this context. Okay. So for the time to go from, so let me write that down actually. So time is equal to distance divided by rate. Okay, so for the time to go from Chicago to San Francisco, the distance is 1,850 miles. And when you go westward, when you fly westward, which this one is, right, heading to San Francisco, it's going to be a headwind. It's going to be decreasing the plane's speed. So we're going to take the plane speed, which is 480, and we're going to subtract the headwind, which we're calling S. This is the headwind. Subtracting it is what helps me slow down the speed of the plane. This is kind of like the combined rate of plane and wind together. Okay, now for going from SF to Chicago, it's the same distance, 1,850 miles, but now you're flying with the wind, so we call it a tailwind, and instead of subtracting from the plane's speed, it adds to the plane's speed. So this is kind of the rate going the rate going west. We can maybe call it the westward rate, and then this is the eastward rate. And we can tell that this one will be faster than that one because I'm going to add the wind to it, and this one I'm going to subtract the wind from it. Okay, so then this is my rational equation here. I've got these binomial factors in the denominators, okay, with my variable. And it might help actually over here to think of this as an improper fraction. So I'm going to do the 4 times 7 plus 3, if you remember that rule. So this would be 31 over 4, because 4 goes into 28 7 times, but then there's 3 left over between 28 and 31. So 7 3/4 is the same as 31 over 4. Okay, so let me rewrite this. Let me clean this up a little bit. So now I've got 1850 over the binomial 480 minus s plus 1850 over this binomial of 480 plus s is equal to 31 over 4. So I need to solve this equation, and so I'm going to use the process we had learned in our Skill 7 video, which is to find a lowest common denominator and then multiply that to everything. Now in this case, there's really nothing in common between each of my denominators, so I'm just going to have to multiply them all together. Because, yeah, they don't have any common factors, so they're all remaining factors. So you just multiply them all together, and then you take that amount and multiply it to both sides of the equation. So all of this, 4 times 480 minus s times 480 plus s, gets multiplied to both sides. So I multiply all of that here, and then I multiply it to this side as well. So first I'm just going to write everything out, and then I'll start canceling. So in this first fraction, I have 4 times 480 minus s times 480 plus s, and then times the numerator, 1850. And all of that is over 480 minus s. And then in this fraction, again, I have 4 times 480 minus s times 480 plus s times 1850 again. So the numerators are pretty much the same, and then that's being divided by 480 plus s. And then on the other side of the equal sign, I've got the 31 from my numerator, and then times all of the same stuff, 4 times 480 minus s times 480 plus s. And then on that side, it was all divided by 4. So I know this looks really crazy right now, but that's because I haven't canceled anything yet. Once I start canceling things, and any common factors will cancel, then it will start to be much simpler. The numbers are large, but the equation that we solve, you'll find, is not going to be that hard. So basically every denominator cancels out, and then in this first fraction, so usually what I do when I have like single factors times a binomial is I multiply the singles together first, and then I distribute later. And here I'll just kind of wait because I'm going to need to FOIL these. And then similarly, when I have one single factor and two binomials, I tend to FOIL the binomials first and then distribute later. So let me do that. So I'm going to do 4 times 1850. And that gives me 7,400 times the quantity 480 plus s for that first fraction. Over here it'll be similar, but it'll be multiplied to the other binomial, 480 minus s. And then here I'll have 31 times, I'll just write everything out right now, and then I'll FOIL in a minute. So 31 times 480 minus s times 480 plus s. So I'm going to go ahead and distribute the 7,400 to each binomial on the right side. And then I'll FOIL the binomials on the left side. I'll distribute the 7,400s, and then on the right side I'll FOIL the 480 minus s and the 480 plus s. So when I do 7,400 times 480, I get 3,552,000, and then plus 7,400s. So and again, I get the same thing, 3,552,000 minus 7,400s. Now, when I FOIL out two binomials with the same numbers and opposite signs, it's basically going to end up being a difference of squares. So I know the two middle terms, this one right here, 480s, and then this one here, negative 480s, will cancel out. So I know it just ends up being 480 squared, which is 230,400. That's 480 squared minus s squared. And then I'll need to distribute the 31 to those two things. Meanwhile, on the left-hand side, I can see that the 7,400 s's will cancel out, and the 3,552,000s will add up. They'll double up. So they add up to be 7,104,000. So the left side just turned into this. And then on the right side, I just have to do 31 times 230,400. And that's 7,142,400. And then I also multiply it to the s squared, so it's 31s squared. So I basically get down to this equation here, which is a quadratic. It's a quadratic equation, but it's not like the like ax squared plus bx plus c quadratic, because there's no s term. There's only an s squared term. So because of that, I'm just going to isolate the square, and then I'm going to square root both sides. It's kind of a different strategy when there aren't any other s's, right? No s here, no s here. In fact, I can go ahead and combine these numbers because they're both constants. So I'm going to subtract 7,142,400 from both sides. Negative 38,400 equals negative 31s squared. So then I will divide both sides by negative 31. Which is good. That turns it positive, because if I'm going to square root, I need the value to turn positive. So dividing these numbers gives me a really ugly decimal. So I'm actually going to leave it as a fraction for right now. I'll just call it 38,400 over 31. And that's what s squared equals. And then I'll go ahead and square root both sides to cancel out the square. And then when I do this in my calculator, I'll turn it into a decimal. So s will approximately be the square root of that fraction. So I do 38,400 divided by 31. And this decimal is like 1,238.7 approximately. So then I will square root that decimal, and that turns into about 35.2 approximately. So the question is, here's my answer, but what is it answering? Like, what is this? So let me box this, and let's look at the very beginning of this problem when we defined our variable. We said that s was going to represent the speed of the wind. And speed is basically, in this case, is miles per hour, right? The speed of the plane was in miles per hour, and so the speed of the wind is also in miles per hour. So basically, this is just how fast the wind is blowing toward the east. So we'll say the eastward wind, speed, I guess the eastward wind speed is 35.2 miles per hour. That's how fast the wind is moving. So that's it for this video. We're going to practice problems like this in class tomorrow, and I'll see you there.